Okay, in this video I'm going to begin section 3.3. We're going to look at the derivatives of the trig functions. Before we get to the derivatives of the trig functions, we need to know two important limits that we're going to be using in the proofs here. The first limit is the limit as theta approaches 0 of sine theta over theta is 1. Okay, and we'll look at the proof of that in just a moment, but the second limit is this one down here. The limit as theta approaches 0 of cosine theta minus 1 over theta equals 0. Okay, so I'd like us to look at the proof of each one of these. In the first one, we're going to need a picture that we're going to refer to when we give our explanation here. So suppose that we have a circle of radius 1. And so the distance from point O to point A will be 1, and this is a part of a circle, if you can imagine, a complete circle. I'm just looking at a part of this. And I'm going to draw another line here from the center to another point on the circle, which I'll call point B, and I'm going to extend that line past the circle there. And at that spot where point B occurs, I'm also going to drop a perpendicular down and call this point C. Here's angle theta, representing angle BOA, and inside I've created a right triangle here. Okay, now I'm also going to connect points B and A and create another right triangle over on the other side. I also want to position point B, this line here, in such a way so that if I draw a tangent line at point B and a tangent line at point A, those two lines will meet at point E, we'll call it, but I also want the measure of line BE and line AE to be the same. Okay, so this theta value is not just any value, okay, it's like specifically arranged so that these two line segments are the same measurement. Okay. Now I mentioned that I'm drawing a line from O to B, but I'm extending that to a point which I'll call point D, and let me also extend the line that is AE past, and where those two lines meet, I'm calling that point D. Okay, now line BE is a tangent line. So that's going to create a right angle here with side BD and side BE. Okay. Also in this picture, I've got a bigger right triangle created. So triangle DAO is a right triangle, and of course that's the biggest one in the picture. Okay. So in the proof, now theta is approaching 0. Okay. Let's assume that theta is an angle between 0 and pi over 2. That's okay since theta is approaching 0 anyway. Now, by definition of radian measure, arc AB is going to be whatever the measure of angle theta happens to be there. Now, in this smaller right triangle, triangle BOC, let's compute sine theta. Sine of an angle is opposite over hypotenuse. Okay, so the opposite side is side BC. The hypotenuse is side OB. Now side OB has a measure of 1, right? Because I'm using a circle of radius 1 in the calculation. So I've got sine theta equal BC divided by OB, or that's going to be BC divided by 1 is BC. Okay. Now, side BC is going to be less than side AB in this right triangle here, because side AB is the hypotenuse of this right triangle, and of course the hypotenuse is always the biggest, has the biggest measure there. Side AB is going to have a measure that is less than arc AB, and BC, okay, that's what I was calling sine theta, that's what that's simplified to be. And arc AB, that is theta. Okay, so I can conclude that sine theta is less than theta, And in this inequality here, if I divide both sides by theta, then sine theta divided by theta is less than 1. Now, of course, theta is a positive number here, so when I divide both sides by a positive, I will not flip the sign. Okay, you only flip the sign when you multiply or divide by a negative. I'm about halfway done with the proof. Okay, now let me say this next. Since theta, which is equal to arc AB, and arc AB is going to have a measure that is less than side AE plus side BE. Okay, those tangent lines are going to have bigger measurements since they're outside of the circle. AE plus EB is going to have a measure that is less than AE plus ED, and that would make sense because ED is going to have a measure that is more than BE, right? Now, AE plus ED is AD, okay? And in this bigger right triangle here, the biggest one, let's compute tangent theta. Tan theta is opposite over adjacent. So the opposite side would be AD, the adjacent side would be OA. The adjacent side, OA, has a measure of 1, so tan theta would be equal to AD. Now, theta is less than AD, and AD is equal to tan theta. So theta would be less than tan theta. Okay? Now, if we also, tan theta could be defined as sine theta over cosine theta. And let me, in this inequality here, multiply both sides by cosine theta and divide both sides by theta. Okay, so cosine theta would be on the left. Sine theta divided by theta would be on the right. That's where this part is coming from. And we've also said that sine theta over theta is less than 1 from our work done earlier. Now, where am I going with all this? So, I've created this 3-part inequality, and I'm going to use the squeeze theorem next. Okay, since the limit as theta approaches 0 of cosine theta would be 1, cosine of 0 is 1, right? You just plug it in. And the limit as theta approaches 0 of 1 is 1. Limit of a constant is always 1. Then the limit as theta approaches 0 of sine theta over theta, which is squeezed between these other two, is going to be equal to 1 by the squeeze theorem. Okay, now that's what I had to show. I had to show this, result here, and I've done that. Okay, now a bit later, actually in the next chapter, we're going to see this same limit again, okay, and we'll be able to do the calculation in one line of work. Okay, so what I'm showing you here is just one option. It's really our only option, though, based on what we've talked about with limits so far. You see, in Chapter 4, we're going to talk about some other things, about differentiation here. But in Chapter 4, limits are going to come up again, and they're going to be useful for some things that we're seeing in Chapter 4 at that point. But limits will come up again very briefly, and something like this limit calculation is going to be handled a lot different than what you see here. Okay, like I said, one line of work and we can be done. Now, another limit that we'll need to know in this section is this one here. So here's another example. Okay, the limit as theta approaches 0 of cosine theta minus 1 over theta, that is equal to 0. The proof of this limit being 0 is not as rigorous as what you see up here. Okay. In fact, I can begin computing without a picture or anything like that. So now, of course, I can't plug in 0, right? I know I can't divide by 0, so there will be some algebraic manipulation going on here. Okay, I'm going to begin by multiplying the top and the bottom by the conjugate of the numerator. We've done lots of things with conjugate already. Okay, conjugate just means that between the two terms, you're going to switch the sign to its opposite. All right, so I'm going to multiply the top and bottom by cosine theta plus 1. And let me see where that takes me here. So in the next line on the numerator, inside the limit, when I FOIL this, I'm going to have cosine squared theta, and of course the middle term will go to 0 there, minus 1 at the end. And now sine squared theta plus cosine squared theta is 1. Okay, so cosine squared theta minus 1, that would be the same as negative sine squared theta. All right, so I'm using that Pythagorean identity to get to the next line here. I still can't plug 0 in, right? But sine squared theta, well, that's the same as sine theta times sine theta, right? So I've got, and the negative can be brought outside the limit here. So I've got negative, the limit as theta approaches 0 of sine theta times sine theta divided by theta times cosine theta plus 1. I'm going to go ahead and split that into two fractions. And I can go ahead and split this into two limits if I want. The limit as theta approaches 0 of sine theta over theta, well, that's equal to 1, right? We just showed that. So I'm using that here in the proof of this other limit. So I'm going to have negative 1 times, now the limit as theta approaches 0 of sine theta over cosine theta plus 1, you can just plug that in directly. There's no problem there. Okay, sine of 0 is 0. Cosine of 0 is 1. So you've got 0 divided by 2 is 0. Of course, I couldn't plug it if I were dividing by 0. 0 times anything is 0. All right, so that would complete the proof of this other limit here. Now we're going to use these two limits for some different things in this section. So let's take a look at theorem next. Okay, the derivative of sine of x is equal to cosine x. Let's take a look at a proof of that. Now, and by the way, before we do that, there was a problem that we had looked at earlier. It was in section 2.8. And I had mentioned in the video that I really liked the problem because it was a good introduction to things that we would see later on. In that problem, we had the graph of the sine curve, and we were talking about the derivative and tangent lines and things like that. And we had sketched the graph of the derivative of sine x, and then they want us to make a guess about the formula that represented the graph of the derivative. Now, the graph of the derivative looked like the cosine curve. Okay, so we had guessed that the derivative of sine x is cosine x. Now, at that point, it was just a guess. Okay, in fact, that is true, though. The derivative of sine x is cosine x. Let's take a look at a proof of that. So the derivative of sine x, I'm going to use the limit definition. And so I got the limit as h approaches 0 of the difference quotient. Now, sine of x plus h, I'm going to use a trig identity. This is not an identity that I would want you to have memorized. It's very easy enough to just look up in a book, okay? And it's a sum and difference formula, okay? So sine of x plus h is the same as sine of x times cosine h plus cosine x times sine of h. All right, so I'm using that identity, and everything else will stay the same. Okay. Now, in the next line, I'm going to go ahead and let's just kind of move some terms around here in the numerator. So let me put this term in front here, and then I'll just put this term that was leading off there at the end. Okay. So just a rearrangement of some terms. Now, with the last two terms, sine x is in common. Okay, so I'm going to go ahead and factor out a sine x from both of these. And the leftover then would be 1 minus cosine h. Of course, if I distribute negative sine x back inside, I'll get negative sine x plus sine x times cosine h. Okay, now the next thing I'm going to do is I'm going to split this single fraction into two fractions. And you can also split that into two limits then. Okay, so the first limit here. The limit as h approaches 0 of cosine x times sine h over h. Well, cosine x would be a constant, right? Since this limit is in terms of h, anything in terms of x can be treated as a constant. Constants can come out of limits. And the limit as h approaches 0 of sine h over h, that's equal to 1, right? That was the first limit that I had shown you here. We get 1 for that. Okay, so I've got cosine x times 1. Right, now I was splitting this into two fractions and also two limits here. Sine x is a constant that can come out of my second limit, okay, since the limit is in terms of h. And the limit as h approaches 0 of 1 minus cosine h all over h, well, so the limit as theta approaches 0 of cosine theta minus 1 over theta, that'd be 0. That was the limit that we had just seen earlier. Okay, now I've got the numerator terms switched. Well, there's no problem with that. You know, if I were to factor out a negative sign, I'd be switching the two terms there in the numerator. 0 times negative 1 is still 0. Okay, so I'm subtracting sine x times 0, and cosine x minus 0 then would be cosine x. So the derivative of sine x is cosine x. Now, using the same methods, it can be shown that the derivative of cosine x is negative sine x. What I mean by same methods is you're going to start with the limit as h approaches 0 of the difference quotient. You'll need a trig identity. It's going to be another sum and difference formula that you can easily look up in a book, okay? And you will need to use these two limits that we had worked through earlier, okay? Limit as theta approaches 0 of sine theta over theta, that's 1. And then the limit as theta approaches 0 of cosine theta minus 1 over theta, that's 0. And so, you know, you could show, if you wanted to, that the derivative of cosine x is negative sine x.